Better?
There you go.
Great. Wonderful. Floor is all yours, JP.
Okay, so can you see my mouse?
Yeah, yeah.
Yep.
Okay, very good. All right, thank you guys for inviting me to talk about this. I haven't talked about this for a while, but we are actively working on it still, so it's an interesting subject. I'm happy to revisit it by giving a presentation. And I will try to stick to the 30 minutes as best as possible. Please, Ming, just cut me off or give me a minute warning or something, and I'll wrap it up. I should first thank Moore Foundation and NSF for funding this work. And this is work done at University of Maryland in our Quantum Materials Center. So I won't go through everyone here, but the main people involved in the work are my former student, Chris Eckberg, who really drove a lot of this work, and I'll mention him as we go, and former student Daniel Campbell, who helped, as well as several other people doing experiments and so on.
Sorry, JP, to interrupt. So I'm seeing partial screen. I don't know if anybody else is.
Yeah, that's the case. Yeah.
Yes.
Seems like it's shifted on the left-hand side.
Okay, let me just, give me 1 second and let me try to second screen only. Okay. Is this my
yeah, presenter mode?
Okay, hold on a second.
It was okay on the title slide, and then and then on the.
Oh, okay. Sorry about this.
This is presenter mode, yeah.
Yeah, sorry, this is such a pain. Okay, while it's thinking, I'll just thank my collaborators. Jeff Lynn, we were doing some neutron scattering early on and saw some very unusual peak splitting at the phase transition. Is this still not?
I don't know if it's still, yeah, okay, let's see. Maybe it's still thinking. To the presenter mode.
Okay, you know what? I'm just going to do this.
That's great.
And,
yeah, that looks good.
Yeah.
Okay, is that better?
Yep.
Looks fantastic.
Yeah, that's good.
Yeah. All right. One day I will figure this out. Okay. Okay. Lots of collaborators. Just to mention, of course, Peter Avamonte, who we did some nice X-ray work with, who will present after me. So that's great. And then several other people who have, over the last couple of years, have been exploring this material with various techniques. And then Raphael, who helped us with some of the theory on the pneumatic phase, and is continuing to work on that as well. Okay, so everyone's familiar with pneumatic crystals. You all watch TV, presumably, and you know that your LCD screen has nematicity in it, right? And so you're reminded every night of nematicity. But in our more isolated world of superconductors, et cetera, we're also familiar with fairly recent appearance of pneumatic order and fluctuations, et cetera, in two very famous superconducting families, of course, the cuprates and the iron pnictides. And it's still an ongoing subject to understand what's the role of pneumatic order, pneumatic fluctuations, and pairing, for instance. That's one of the main motivations we had in doing our study. And then of course, this seminal work by Ian Fisher's group on developing this very nice technique of elastoresistivity to study nematicity or pneumatic order or pneumatic fluctuations directly using a fairly straightforward technique has really opened the field, and several of us, have exploited this exact technique to do such studies. And this is what I'll show today. And of course, the work that Ian's group did was on Jun Hao in particular, was on the iron pnictides, which really opened our eyes to the role of pneumatic fluctuations in the system. And that's been explored in several variations of the iron superconductors, which I'll just flash here. And one of the key things about pneumatic order or nematicity is understanding its role in the presence of other orders and other phase transitions. And so, when a crystal breaks rotational symmetry, there's in essence 3 different types of properties that are affected that break the corresponding symmetries in structural, order, orbital, and spin. And usually we're familiar with the sort of trivial case where structure will change its symmetry and then the other 2 follow along. But there are cases now known where something like orbital order leads the way and the other ones follow along. And this is the non-trivial case that we're discussing here. And then the motivation, as I said, is to understand the role of this type of fluctuation in pairing. And this has been explored for a few years now, in particular by Steve Kivelsen's group and Sam Lederer, who has been continuing to study the effect of pneumatic fluctuations on superconductivity, whether it's driving the pairing or it's enhancing the pairing. That's the latter is what we think is happening in this nickel arsenide system. And there's key questions, of course. So, how much can TC be enhanced? The Q equals 0 symmetry, which is unusual type of fluctuation symmetry to think about in pairing. And then the role of dimensionality. These are all questions that still need to be answered in general. So a long time ago, actually, we were looking at this nickel arsenide system for other reasons, because first of all, it was explored right after the discovery of the iron superconductors, in particular, because if you look at the resistivity, for instance, of barium nickel arsenide, it looks identical to some of the iron pnictides, but in fact, it's not. It undergoes a structural transition, and there's no magnetic order. And so actually this first order transition is structural in nature. And it goes from a tetragonal phase, which is the same as the iron pnictides, to this triclinic phase. It's very unusual, very unusual transition to go from tetragonal to the lowest symmetry phase at low temperature, but that's what happens. And it is also a superconductor. So at TC below about 0.6, 0.7 Kelvin, it becomes superconducting. And this was studied fairly quickly, for instance, by Los Alamos, Bill Ronning and company. And they fairly quickly concluded that at least the nature of the pairing is at the very least a fully gapped superconductor, as shown by thermal conductivity and so on, specific heat. And so it was kind of dismissed as something not very interesting. Of course, there's the strontium variant of this material. You can also make strontium nickel 2 arsenic 2. It's tetragonal, shows no phase transitions, and it looks completely boring. The resistivity looks metallic. It's also a superconductor, ironically, but with almost the same TC. And it also looks fully gapped and conventional, at least according to thermal transport and specific heat. And so, one might conclude fairly readily that TC is the same, perhaps the phonons are exactly the same, and it's just a BCS superconductor. Although you have to remember that one is triclinic and one is tetragonal, so it's a bit unusual. So early on, we sought to explore this transition between the two to see what happens in between. Something interesting happened. For instance, the C-axis changes quite dramatically. It changes by 10% from one side to the other in the tetragonal phase. Of course, there's the triclinic transition that occurs. So, and yeah, I should remind you that the triclinic phase, you know, this is the lowest symmetry phase. So all the angles are off 90 degrees. All the bonds, A, B, and C, are all different. You know, so it's the, you know, it's the most monstrous tetragonal phase you can think of. And so we did several studies, and here's, you know, sort of the answer. To start with, we studied, for instance, electron doping the nickel system, and we found, for instance, that TC gets enhanced as you add cobalt into the system, and you suppress this triclinic phase. And this was known through other systems by Nohara's group and company in Japan, where they studied, for instance, copper and phosphorus substitution. Although those systems, I can comment later if somebody asks, those systems show a sort of a first order transition from one phase to the other. And then the strontium system we studied, and you know, here's one of the answers, that TC gets enhanced quite a bit also in this system. And I'll explore the second one a little bit more. So Peter will talk presumably a little bit more in detail about the charge order in the system, but just to introduce it, the structural transition that occurs at about 135 Kelvin is very abrupt, first order. You can see tetragonal phase to triclinic. And what was found by Peter's group is that actually there's also a charge order coming along for the ride. Not only does it appear in the triclinic phase abruptly, but it starts to appear in the tetragonal phase. And these are two different charge orders. And it's even richer than that, which Peter will elaborate on. And so just to show, for instance, the two charge order phases that were discovered, the triclinic phase happens at 135 Kelvin. There's an incommensurate charge order that slowly grows from higher temperature and peaks just before the triclinic transition. It dies, and then there's a commensurate charge order that builds, the red curve here, in the triclinic phase. And originally we thought, the original data showed that we thought that this incommensurate order was breaking with the tetragonal symmetry, but Peter's going to show, I'm sure, the fact that it actually doesn't, has a 4Q, has a multi-Brillouin zone modulation, which was actually hard to see in the first experiment. Okay, so the experiments we did in Maryland were this classic elastoresistance experiment where you take a crystal, glue it on a piezo stack, and strain it. And you measure the strain, and you do all the usual things, which I won't go into now, to make sure you're doing it properly. And you can do it two ways. So, and this is to measure different symmetries. Actually, three different ways you can do, but there's limitations on the way the crystals are grown and shape and size. So we do two of them. And this is the classic orientation of the crystal on the piezo stack, for instance, in the iron-based superconductor studies. This is the first experiment we did, and my student, he built the apparatus, did the experiment, did the measurement, and basically found that it was zero. And we said, okay, let's move on. And let's study something else. And a few months later, he happened to, just on his own initiative, measure the other direction, which is the B1G direction, where you have two crystals. And there's other ways to do this, but this is the way he did it. And lo and behold, he actually found a huge pneumatic susceptibility that grows as you approach the triclinic transition. And so I was very happy to see that, of course, very surprised. And not only that, but the magnitude of it, if I go back one, compare, this is about 60 in these units of the susceptibility. It's the same order of magnitude as the iron superconductors. So it was very nice to see that, and very surprising. We had no idea we were going to see this kind of thing. Just to compare the two, this is one experiment, it's an older one. But you see that the two symmetries probe the two experiments probe the two different symmetries, and certainly it's the B1G that showed a large signal. And that was surprising because the iron system shows the large signal in the B2G. And you can see here, this is a fancy way to show that there's a rotation of the response in the two systems. And so just to remind you, in the iron systems, the B2G pneumatic amplitude is at least most likely tied to magnetic correlations along the 110 direction. Whereas in the nickel system, there is no magnetism. And so the question is, what is related to this? And this is ongoing study. Perhaps it's charge order, perhaps it's some orbital ordering or susceptibility to orbital ordering and so on. Okay. In these experiments, the other thing we found in barium nickel arsenic was that, so here's sort of the raw data of this experiment. You measure the resistance response as you apply strain on the x-axis. 0 is here, so you go through 0. And it's basically just like a magnetic susceptibility measurement. You measure a slope, and then the slope is the susceptibility. Now, the thing here is that you see with your bare eye that there's these loops in some of the data. And a loop is just like in magnetization, it's a hysteretic loop, which signifies some type of domain structure, which signifies some type of order. Now, this is the nematic response. So we were surprised to see this, and we concluded essentially that this seems to be tied to some kind of nematic order, not just a fluctuation. And it has a temperature dependence. You see that at higher temperatures, like in the black, there's no hysteresis. It's just a flat line. You go up and down as much as you want, and it's a slope. Whereas as you approach, basically below about 150 Kelvin, you start to see this loop opening up. And you can traverse this loop as much as you want. It has hysteretic behavior. This region, as I said, is about from 155 Kelvin down to the triclinic phase. And you can see it's in this range here. Interestingly, this is roughly speaking also the range, well, actually almost identically, also the range where the charge order appears, this incommensurate charge order. So charge order onsets gradually, and this nematic order onsets gradually. And in fact, you can plot them together. This is in the paper. Shown in the red and blue, you can plot the width of the hysteresis. It's just some measure of the order that we have, along with the square of the intensity of the charge order peaks in the red. And they actually track each other quite nicely. So it shows a linear relationship between these two. And this is we're still understanding what's happening here. For instance, there's new evidence that the charge order, as I said, is not breaking tetragonal symmetry. So we have to understand the symmetries that are being broken by these orders and how they're coupled, because that will help us understand the connection between the two. And then the nematic susceptibility, you see that it actually starts to grow before this order onsets, and then peaks, of course. So this actually, it may look like a Curie-Weiss behavior, but it's not. It's actually a little bit different. So, and it's shown here. And now what I'm showing is the progression of this nematic susceptibility in order as a function of strontium substitution. And so here's the phase diagram showing the triclinic structural order being suppressed as you add strontium, as you replace barium with strontium. So at some point, about 70%, there's a cutoff, and it's completely tetragonal. There's no triclinic order. And then as you go along this x-axis, you see that the nematic susceptibility, its growth gets suppressed in temperature as well, and its magnitude gets suppressed until basically at x equals 1, the strontium end, there's nothing. It's just completely flat. Now there's some structure in here, and you can look at this more carefully. And for instance, this is scrunched down just to compare scales, but in the pure barium end, this is the data, and the light gray area is where we see this nematic order, the hysteresis. And you see that actually progresses as well. By the time you get to 0.6 or so, there's no hysteresis. And I'll show you that there's also no charge order above the triclinic transition. And that's the point where also this nematic susceptibility becomes more Curie-Weiss-like. In fact, the dashed line is a Curie-Weiss fit. Until finally you get rid of the triclinic phase, and there's still a growth, but then it gets suppressed as you go down. until you have nothing on the side. Okay, so it's a rich system. If you put this, oops, oh yeah, I should point out that at this point here, 0.75, and I can come back to it if we have a few minutes, there's actually not a sharp peak, and there's no order that occurs here. Nothing we've measured has indicated any change, any kind of phase transition, but there's a broad maximum in pneumatic susceptibility. And we believe this may be some kind of glassy behavior or something, but it's a bit hard to get at, and we're still studying that. So if you put all the pneumatic susceptibility data onto a color plot, along with the other data, this is what it looks like. So the color contours here are indicating the magnitude of the pneumatic susceptibility. And then the phase boundaries show, for instance, the blue dots are the structural transition. These squares and circles here are where the pneumatic and the charge order onset. So red dot is the charge order, and the blue squares are the pneumatic. The order is indicated by the hysteresis onset. So you see they track each other quite well, and they both disappear around 0.6. And there's no charge order above the triclinic phase here, and no pneumatic order. So they're strongly tied. They're very closely tied together. And then, as I said, at 0.7, you get cut off, and there's only a pneumatic, very strong pneumatic susceptibility that actually peaks before it starts to go down as you approach 0. And then that dies off, and then there's basically nothing. So, you know, even removing all the complications of what's going on here, a very rich phase diagram. Basically, I in hindsight, we should have, for our paper, we should have focused just on this part here. It's all tetragonal. There's no triclinic distortion. There's no charge order. There's no pneumatic order to be seen. There's just pneumatic susceptibility, and there's superconductivity. So I'll show you what happens now in the superconducting state as you approach, well, as you go. But really, you know, this is the interesting part here because it's void of any other complication. Okay. I should go back here. So we with Raphael, we developed a story to understand how this trade-off between this pneumatic order and fluctuation as you go across this phase diagram and the structural order. And they came up with a free energy model trying to understand how you might transition from a structurally driven to an electronically driven phase transition, structural phase transition. But this is going to be modified now that we understand that the charge order is a little different than what we thought of before. So we have to work on this. So now in the last couple minutes, I'll just go through the superconducting state data and again address this question of what happens to TC in the presence of this pneumatic order. In particular, in the absence of magnetic fluctuations, which are good for superconductivity, but they also complicate the understanding. We have a nice clean system that seems to show only pneumatic fluctuations. And the question is, what happens to superconductivity? Well, long story short, we see a dramatic enhancement in TC. So here's the end member, where TC is only 0.6 Kelvin. And as we approach this sort of quantum phase transition, we see TC go up to as high as 3.5 Kelvin, which is not a big TC, but it's 6 times bigger than what it is on the other side. And so, for instance, you can see that the superconducting state is very well characterized. It's a bulk transition, et cetera. Nice transitions and everything. So, as I said, there's some complicated behavior on this side. Now I'm showing the TC versus X, just expanded here. You see that it's very flat for quite a long range, and then there's some funny business here. And the funny business is that the resistive transition is way up here, whereas the specific heat transition is down here. So this is another story which I can address if we have time for questions. But as I said, if you just approach from the X equals 1 side, where this is a boring metal which does nothing, and you approach this hot spot here, you see that TC grows dramatically. And this is what I'm saying. This growth goes in parallel with the very dramatic growth of the pneumatic susceptibility. So in essence, this is the story right here, that we're growing this and this together. Is shown by, no pneumatic susceptibility, a very strong one here. And in parallel, we're of course looking at the superconducting state to see if there's other ways to explain the enhancement of pairing. There basically isn't. The gamma doesn't change, the density of states doesn't change, and the phonon, at least according to specific heat, the phonon slope, the Debye temperature, et cetera, does not change. So there's no evidence of just some enhancement of TC due to conventional mechanisms. So in the end, we had to conclude that it has to be due to enhancement by the pneumatic pairing. So we don't believe it's driving the pairing. We believe that, for instance, if I go back at x equals 1, this is an electron phonon superconductor, as far as we know. But with phonon driven pairing, but as you approach this hotspot here where the pneumatic susceptibility is very strong, it's enhancing the pairing. And again, that's the types of theory that Sam Lederer's company have been working on to try to understand that enhancement. We're considering other experiments to try to explore that. Okay, so that's the talk in a nutshell. So these boring low TC superconductors can sometimes be interesting. Don't dismiss them so easily, and be persistent. This is a project I started 10 years ago, probably. And, nobody wanted to ever work on it, but I said, there's something interesting here. You got to go with your intuition. And we found something quite interesting there. What I like about it, officially, is that there's no magnetic order to be heard of in this system. And that, that simplifies greatly the interpretation of where the enhancement and pairing is coming from, and understanding the different roles of different degrees of freedom in the system. The charge order is quite complicated and quite robust, and Peter will elaborate on that in the next talk. And I'm, it's intimately tied to the pneumatic order and fluctuations, I'm sure. What role each of them plays, what drives the other is an open question. And then, of course, the enhancement of superconductivity is really one of the interesting things in the system. And so thanks for your time, and happy to answer any questions.
Thank you very much, JP. For this really interesting talk. I have some questions, but I guess Paul raised your hand. So Paul, you can ask.
Hi, JP. Could you elaborate on the splitting of the transition in this panel B here that you alluded to earlier?
Yeah, sure. I'm not sure if I have a slide. No, sorry. Okay, so yeah, so as you can see, okay, everything's well behaved up to about 0.5. And then we start to see an enhancement of TC as measured by resistivity. It seems to be like a dome shape here. But if you take the same sample, let's say right below this cutoff, and measure, all three types of measurements: resistivity, Meissner effect, and bulk specific heat transition, they actually show, and this is in our paper, you can look up an example. They show distinct onsets of the transition. So these two are kind of close together. Like, for instance, where resistivity goes to 0, the onset of susceptibility, I think, occurs. So that, that's not unusual. But the bulk transition is way down here. Now, Peter has, I think we'll discuss a proposal for what might be happening here in terms of why there is some enhancement of a sort of filamentary type superconductivity here. And so, stay tuned for that. But once you get on this side, everything's well behaved. All the transitions are as they should be together, and that that tracks through here. So that's what we know about it so far.
Great, thanks.
And then Peng Zhang.
Yeah, so the crystal structures are identical. I mean, from 0.1 to 0.75. I mean, there's nothing changes in the lattice. So what about, yeah, are there any?
You mean in the triclinic phase?
Yeah, in the not triclinic phase. I mean, on the left, I mean, the most boring one, you said it's It's a
Oh,
tetragonal.
from
phase,
one
right?
to, yeah, no,
Yeah,
it's
yeah, yeah.
tetragonal. Yeah, there's
So
no,
it's nothing
there's no
happens.
phase transitions that we've seen here except for superconductivity.
That's very, very odd. So then you still see pneumatic susceptibility change. The near
The
0
pneumatics,
point.
yes, yeah. Now, there's a subtle thing that happens at this crossing here. And
Mhm.
actually, that goes to the original reason we studied this. I was trying to see if there was a tetragonal collapse occurring across here, like in the iron systems. Because as I said, there's a 10% change in C. And over here, you know, the arsenics should be bonded, actually. They should form dimers.
Mhm,
Now,
mhm.
in this system, I think that does happen here. We have some X-ray data that shows that in the paper. But it's a very subtle transition. It's nowhere near what happens in iron. So for instance, the tetrahedral bond angle shows some change at this point, but it's not an abrupt first order gigantic transition.
Are there any? Have you looked at the phonon anomaly? There's no phonon anomaly.
I'm sorry, what?
Are there any phonon anomaly? Compare with
Phonon, you said, or
yeah,
thermal?
no, phonon, yeah. Lattice, I mean.
No, not that we know of.
Okay, thank you.
Timel?
JP, I was just wondering about the pneumatic order, 140 Kelvin. That seems like a very comparable temperature with the ion case. So FESE used to be the poster child of only pneumatic order, but we know that it has a lot of things in it. I was just wondering whether you mentioned neutron scattering at the beginning of your talk, whether there's any knowledge about the inelastic neutron spectrum?
Inelastic neutron.
Yeah, he said no, right? I mean, I asked him. That's the phonon, right? Yeah.
No,
So,
well.
Yeah, so the older data, was elastic data. I don't know, Pencheng, some time ago, you told me you looked all over for
Yeah,
stuff.
there's no magnetism. We know that. That's why we never publish anything.
So there's no spectral weight whatsoever that can be seen.
No. I mean, we it was a student, and the student had graduated. Yeah, after that, yeah.
But the potassium ion to arsenic 2 was said to have very weak magnetism, but I think that story is still evolving. I'm just wondering whether it's interesting to go back to look at this.
Well, with inelastic, perhaps. I'm not sure that's been done.
No, but
Certainly
that's
not
the whole
across
point.
the phase diagram.
In FESE, if you look at the inelastic spectrum, the total spectral weight in the spin sector is actually larger than barium ion to arsenic 2, right? So one might.
So did Jeff do inelastic scattering on these, or Jeff has not?
No.
Okay.
Okay, thank you.
And he won't for another year or two.
Okay.
Christoph?
Yeah, very, very nice talk. I would like to just mention that we have very clear evidence for two phase transitions in the nickel system. So one right at sort of the incommensurate charge density wave, where the fourfold symmetry is broken. You have probably an orthorhombic phase before you enter the triclinic phase. So the incommensurate phase is not, I don't think is tetragonal.
I see. Well, so please, let's see. Peter will have something to say about it.
So Christoph, is that for the N number? Sorry, or can I ask, is that for which doping is that?
The paper is on the archive if anybody's interested.
Okay.
Yeah, I mean, was definitely an open question for us. There's a very subtle
I think it's
orthorhombic distortion, as you would expect, right? Yeah.
So,
but let Peter can address this in his talk.
Okay.
At least from his perspective.
And then I think it was Andre.
Yes. Yeah.
PP, very, very nice talk. Is there anything you could tell us about what's known about the symmetry of the superconducting state? For instance, quasi-particle interference in STM. I guess nobody done laser ARPAS. Do we know anything about specifically inside the triclinic charge density wave phase?
Okay, you're asking about the superconducting state or the?
Correct. The superconductor. So, you know, below
Yeah, so the
3
TC is
Kelvin.
quite low. I think it'd be hard to do any kind of ARPAs to study that state. STM, we tried with a few people and no one has been able to get reproducible data yet,
Mhm.
but that would be nice to do. And the conventional probes like thermal transport and so on, you know, I showed the end members, there's no evidence of anything other than a fully gapped system.
Mhm.
And at least via specific heat and the, you know, where TC is enhanced, it also looks fully gapped, at least according to specific heat. So we don't see any evidence of unconventional superconductivity so far.
I see. And that conclusion is the same on the left and on the right of the triclinic to tetragonal transition?
Yeah, in terms of it being fully gapped. Yeah.
I see. So you do not see anything special happening at that point, just mainly TC changes a little bit.
Correct.
Okay, thanks.
And I think we have Han.
Yes, I had nearly the same question. I wanted to know whether the gap followed TC on the right-hand side.
The gap, yes. So the, at least according to specific heat, yeah.
Yeah,
Yeah, everything is well behaved, ECS like.
but still it's strange that it changes so fast.
Yeah, that's right.
Because
No,
it's
to me,
a
this is
standard
the most
factor
amazing
6.
thing about the system, but
You say a factor 6, so it's a huge effect.
yeah, that's right.
So you see it being fully gapped and regular, but still with a change of factor 6, which you attribute to nematicity in some sense.
Yeah, because there's nothing else that really changes. So, you know,
Yeah.
specific heat is our main probe of that. We would like to do other experiments, for instance, thermal transport, but I don't expect, I didn't show the low temperature part of the specific heat, but it looks.
You get the gap from the low temperature part.
No, I'm talking, no, the gap I'm getting from just the jump at TC, for instance.
The magnitude of the jump.
Yeah, yeah.
Okay.
If we can take one last question from Amir, and then we'll move on to Peter's talk. Amir?
Yeah. It was a very nice talk. I have a question regarding the two systems, strontium nickel to arsenic to compared to the barium one. So can you say something about the enhancement of the TC? If you dope the system in the nickel arsenide planes with phosphorus, the TC goes up at the critical doping to 3.5 Kelvin, pretty similar to if you dope the system on the barium side with the strontium. Do you have any idea why is it like that? Why are these TCs so similar, although you are doping completely in different sites and different pressure effect?
So yes. So first of all, I don't call it doping because they're isovalent substitution. So yeah, even including phosphorus and arsenic. But so the difference here is really in this end of the phase diagram, because if I think about phosphorus substitution, which was studied by Nohara and company, if you take the end member, barium, nickel 2, phosphorus 2, TC is 3 Kelvin. So it's more like, you know, if I think of this as phosphorus, the TC is flat, 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 and then it jumps up and then it's flat, you know. So once you cross to the, once you cross the phase boundary, the structural phase boundary, the TC jumps up. I don't have the data here to show, but that's my recollection of it. Whereas, you know, as I said, this end of the phase diagram is really telling because there's no phase transition, nothing's changing except the pneumatic susceptibility. So TC starts at 0.6 and goes up to 3.5. So this is the contrast in the phosphorus substitution. Of course, I'd like to study the phosphorus substitution series as well to see what happens with pneumatic susceptibility. That would be fun.
Okay, thank you.
Welcome.